Hi. If we want to move one place to another, we need some mode of transport like bicycle, bike, car, train, etc. In the same way, computer requires the ability to exchange information among wide variety of devices. Data transfers may take place with full or minimal involvement of the processor. For transferring the data among processor, memory, and input-output devices, an interconnection network is used, and the most commonly interconnection used is called a system bus. In simple structure, a bus acts as the interconnection network between the processor, memory, and input-output devices. Only one source destination pair can use this bus for transferring data at any instant of time. The sets of lines are used by the bus for carrying address, data, and control signals. The sets of lines are used by the bus for carrying address, data, and control signals. These lines are connected to the input-output interface for an input-output device. Each and every input-output device is given a unique set of addresses for the registers in its interface. The address decoders of all the devices on the bus decode and examine the address placed by the processor on the address lines. The device recognizes this address and responds to the various commands issued on the control lines. These command lines are used by CPU to request an operation, either a read or a write, and the requested data is transferred on the data lines. When the input output devices and memory utilize the same address space, it is known as memory mapped input output. Any instruction that has access to memory can be used to transfer data to or from an input output device. Load command can be used to read from the input device, and store command can be used to transfer data to the output device. For instance, load instruction reads from the data in and stores them in processor register R2. Load R2 data in, store R2 data out. Similarly, store instruction sends the contents of the register R2 to the location data out, which can be the data register of a display device interface. Moving to the bus operation. Bus protocol comprises set of rules that governs how the bus is used by various devices. The bus protocol decides when a device can place information on the bus, when it may load the data on the bus into one of its registers. Control signals implement these rules and indicate what and when actions are to be taken. There is one control line which is generally labeled as RWC, which specifies whether a read or a write operation will be performed. When RWC is 1, then read operation is performed, and when it is 0, then write operation is performed. Other control lines indicate the required size, whether it is a byte, half word, a word. Bus control lines also carry the timing information to signal when the processor and input-output devices can place or receive data from the bus. In a data transfer operation, there is a master, that is, a device that initiates data transfer by issuing read or write commands on the bus. In a data transfer operation, there is a master, that is, a device that initiates data transfers by issuing read or write commands on the bus. The device addressed by the master is referred to as a slave. I. Synchronous bus. On a synchronous bus, all the devices derive the timing information from a control line, which is known as bus clock. There are two phases of signal on this line, a high level followed by a low level. These two cycles constitute a clock cycle. The first half of the cycle between the low to high and high to low transitions is often referred to as clock pulse. An address and data lines are carrying both high and low signal levels at the same time. This is a common convention indicating that some lines are high and some are low, which depends on the particular address or data values being transmitted. Crossing points in this pattern depict the times at which these patterns change. Signal lines at a level halfway between the low and high signal levels depict the intervals during which the signal is unreliable and must be avoided by all devices. For instance, consider the sequence of signal events during an input or read operation. At T0, master device puts the device address on the address lines and sends a command on the control lines indicating a read operation. Length of the operand that has to be read can also be specified in the command. The physical and electrical characteristics determine the speed of data traveling in the bus. The width of the clock pulse T1 to T0 must be longer than the maximum propagation delay over the bus and longer enough so that all devices could decode address and control signals, and slave devices can respond at time T1 by putting the requested data on the data lines. At T2, the data is loaded into one of the registers by the master devices. Data must be available for a time period longer than setup time of the register so that it can be loaded correctly into a register. Figure 4 somehow paints a more realistic picture of what actually happens. In this figure, two views of every signal can be seen. Signal transition can be seen by different devices at different times, and that is because signals travel through different devices at different times. First part of the figure shows the signal seen by a master, while the bottom part shows signal seen by a slave device. Master device sends the address and command signals at the start of the clock signal at T0. As a result of delay in the electronic circuit output from the master to the bus lines, these signals appear actually on the bus at TAM. Signals reach the slave at TAS and at T1. Slave decodes the address and sends the requested data. Now the data signals appear on the bus at TDS, and after traveling towards the master, they arrive at TDM. The data is loaded by the master into 8 registers at clock cycle T2. Thus, the period T2 to TDM must be greater than the setup time of the register. According to the requirement of the register, data is valid even after T2 for the period equal to the hold time. Asynchronous bus. Handshake protocol is used to control data transfer between master and slave. The signals are exchanged between them. Master sends command signals and slave sends response signals. Master assets signals called master ready to specify that it is ready for data transfer, and the slave assets slave ready signal as response to master. Handshake protocol. The address and command information for data transfer is placed on the bus by master and activates master ready line to indicate all devices. Then all the devices can decode the address and selected slave perform operation on data. It activates slave ready line to inform the processor. Till then, master waits for the signal. If read operation is performing, data get loads into register. Timing of data transfer using handshake protocol is explained below. Let us discuss the sequence of events. T0. The address and command information is placed on the bus by master, and other devices can decode the information. T1. The master activates the master ready line to 1 and informs other devices that information is ready. The delay is introduced between T1 to T0 for skew And skew occurs when signals are transmitted from one source to destination but different times because each line has different speed of execution. It assures that master ready signal does not arrive before command information to other devices. T2. The slave which is selected perform the operation by decoding the address and command information and place the data on data lines and activate the slave ready line. In case due to circuitry extra delays are introduced, then slave also has to delay the slave ready signal. So the period between T2 to T1 is the distance between master and slave signals and delay introduced by the circuitry. T3. When input data is placed on data lines, master allow for bus skew. Here skew is allowed due to setup time needed by register. So this delay is equivalent to maximum bus skew and minimum setup time, and master loads the data into one of the processor register. After this, master activates master ready signal to specify that it has received the data. T4. At this time, after receiving data, it removes all the address and command information from the bus, and delay between T3 to T4 is for bus skew. Some other device can also change address on the bus when master ready signal is 1, so errors can be generated. T5. Device interface remove the data and slave ready signal from the bus when master ready signal changes from 1 to 0. The input operation is complete. Timing information of the output operation is same as input operation. Here, master places the output data on data lines and activates the master ready signal. So address and command information is now transmitted from other devices. The selected slave loads the data into one of the processor register and activates slave ready signal to 1. Rest timing signals are the same. Both the handshake signals are said to be fully interlocked because change of one signal change others. This is known as full handshake. That brings us to the end of the section. Thank you and see you in our next section.